So Tari, welcome. Thank you for joining us.
Thank you.
Please feel free to introduce yourself and share your screen and get started.
Sure, I'll share my screen. Okay, so right, hello everyone. So I'm Tari and full stack developer with Randamu. We're mainly focused on the.
Oh, by the way, just a sec. We can see the little pop-up screen of the video. If you close that on your screen.
Okay.
Yeah, amazing.
Right. Okay. Cool. Right. So yeah. So just intro again. So I'm Tari and yeah, a blockchain developer with Randamu. Today we'll be going through a couple of our products that we've been building, and we currently have live on the Filecoin testnet. So I'll just walk you through a brief demo of the randomness. You can request randomness on chain into smart contracts. Again, that's via our threshold cryptography and threshold network. And then secondly, we'll then go through a demo of a simple sealed bid auction smart contract, which uses Timelock encryption on chain. So that's the sort of plan for the workshop. Okay, so firstly, just a brief walkthrough. So building a decentralized threshold network. Through that network, we're then offering verifiable randomness, which can be consumed on-chain. So there's several applications of randomness on-chain. So you could use it in gaming to maybe issue like random skins or rewards within games. And then we also have Timelock Encryption, which you could use to ensure that data remains encrypted within your on-chain smart contracts until a future block number as well. But you can also encrypt towards other conditions as well. So it could be based on smart contract events happening, or some other real world conditions also. Right. So we're going to be using a few resources within the workshop. So the main GitHub repository that we'll be using is this one. I'll just share the link in the chat window. And then we also have a blog post which was published recently, which I'll also share as well. So that will be the walkthrough that we're going to be working on. So those two repositories, so that repository, the GitHub repository, and then the blog post as well. And then I'll walk you through the steps. All the smart contracts that we're going to be using are all deployed on the Filecoin calibration testnet. So you'll be needing some test tokens, some test FIL tokens in your wallets to pay for transaction costs. So I've just pasted a link to the token faucet as well. So it works with your EVM wallet address. You just request funds, paste your EVM wallet address, and then they'll send 100 FIL tokens to your wallet. Okay. So I'll open up my Visual Studio Code, which is where I have all the source code that we're going to be using. When you clone the repository, it should give you this sort of structure. So you'd have the source folder, which contains the two smart contracts. One is for the randomness example, so just requesting randomness on chain. And the second one is for the simple sealed bid auction smart contract. With the sealed bid auction smart contract, we're going to be building an auction contract, which allows people to place encrypted bids. And those bids will then be decrypted at the end of the bidding window. And then once the decryption happens, everything on chain, all the decryption happens on chain using BLS cryptography. Then the smart contract automatically works out what the highest bid amount is and also the highest bidder address as well. So we'll go through everything also. So I'll just show you the randomness example very quickly, and then we'll then walk through the sealed bid auction step by step as well, using the blog post article. So for the randomness smart contracts, we have a Solidity library as well, which is available on GitHub. So it's a randomness Solidity GitHub repository. To derive randomness on-chain very quickly, we just need to set up like a simple randomness consumer. So this could be a game, an on-chain game, which you could use to maybe roll a dice or pick random indices from an array. And then when you declare your contract, you need to install the randomness library and then inherit the randomness receiver base abstract contract, which is a contract that receives the randomness and the callback from the off-chain oracle. And then in the contract, we define the address of the randomness sender, which you're going to be calling to make randomness requests as well. And then we define two variables. So we're just keeping track of the randomness that we receive and the latest request ID from the randomness request. And then we have a roll dice function. So in this function, we're just making a request for randomness, and then we get back a request ID as well. And then when we make a request in the next block, we should receive a callback with the random value. So we receive a byte 32, which you can then use in another library within the same repository that I just shared to derive values from either an array or to shuffle a dice or roll a dice, for example. So the first steps for the randomness is to we'll deploy the contract. So I've just written like some commands. And then, yeah, I'll just deploy the contract to the Filecoin testnet. So what I'm deploying is the randomness contract. I think it needs the... So I think I need to compile. All right, so it's sealed bid auction. Okay. Right, so I just remove these comments for a minute. Okay, so so I just need to deploy the randomness contract. So randomness consumer script. Yep, randomness consumer. Okay, so I just initialize the variables that I'll be using, and then the private key as well. So just check if everyone's able to clone the repository. So there's a sealed bid auction Filecoin testnet repository. Does everyone have the repository pulled locally or any issues? I can't see any questions in the chat as well. Okay, so I just set the private key for deployment. Private key. Yeah, so that should deploy the contract to the Filecoin testnet. So I'm just deploying the randomness consumer, which should be within the tutorial repository. So just to demonstrate how we can get randomness from the network. So you might get some issues with deploying the contract to the Filecoin testnet. But if you do, you can add a gas multiplier just at the end of the deployment script. So I'm using Foundry Forge script just to deploy the randomness consumer contract. And I'm using the randomness consumer script in the script folder within the repository. Okay. So it does take a couple of seconds to deploy. Yeah, so I think we could just try with a bit more gas. Yeah, I think I have an existing contract, so if this deployment fails, I'll use that one as well. Just give it a few seconds to deploy. Okay, so right. So in the existing contract, we have a randomness consumer contract. So I'll just check the last request ID that was made. So we can see it's request ID 20. And we received the randomness from the testnet, the Filecoin testnet. So we got a byte 32 string. But we can make a request as well. So when we call the roll dice function, it makes a request to the Randamu randomness sender contract off chain, and then the threshold network would send the latest signature, which serves as the latest randomness, and that's then used within the smart contract to derive random values or to roll a dice or shuffle an array or pick random indices from an array. So just sending a transaction to get a new request ID and also a new value for randomness from the randomness sender contract. So the Filecoin testnet, the transactions do take some time. Okay, so we made a new request for randomness. So the previous request ID was 20, and then the previous randomness value is ending with 20 FDE. So just check the latest request ID from the randomness consumer contract. So it should have changed from 20 to 21. And then if we check the randomness value as well, so the last one is 20 FDE. Can check it again. Right, so still waiting for the next block to be mined, and then the off-chain agent should be sending a callback with the randomness value. We can also check on the Explorer. Okay, so there's a pending transaction from the off-chain Oracle. So just making a callback to the randomness consumer contract with the latest value for randomness. So once the transaction is mined, the randomness consumer should be receiving a new value for the randomness, and it can then use that in a larger context. It could be within a game, for example. That could then be used in addition to the library in the randomness solidity repository. So there's a library for shuffling. So you can use the randomness input as to shuffle an array, also as a seed, but you can also use it to pick select random indices from an array as well, with the bytes 32 random bytes. Okay. Okay, but I think the transaction is still pending. Okay, so the transaction has just been mined. So we can do a check again. Okay, so we got the randomness value from the off-chain Oracle. which is received from the threshold network. So the previous value was ending with 20 FDE, and then the new one for request ID 21 ends with 29DE7. Okay, so just a quick intro to our randomness smart contract on the Filecoin testnet and Oracle. So it's quite easy to integrate. So you just need to inherit the randomness receiver base contract. And then you can call the functions which have already been implemented in the base contract, which is the request randomness. And then very easily, the off-chain Oracle then makes a callback to the onRandomness received function, which is internal, but you can override that and then implement your own custom logic as well. Okay, right, so I just close that one. And then the main contract for the workshop was the Sealed Bid Auction smart contract. Has anyone not been able to clone the workshop repo from the tutorial? I'll just check in the chat window just to see if any. I just paste the link again. So it's this repository for the Sealed Bid Auction smart contract. And then the steps for the tutorial will be in this blog article. Okay. So just feel free to shout at any point in time if you're stuck as well. Okay. Right, so just to reiterate again, with the Sealed Bid Auction, the feature from the Randamu network that we're using is the Timelock Encryption. So we just had a brief overview of the randomness feature. So with the Timelock Encryption, we're encrypting data, and the condition is that at its future block number, we'll get a decryption key back to our smart contract. In this case, it's the auction smart contract. So when we get the decryption key, automatically the decryption of the data would happen on-chain. And then in this context, the smart contract then works out the highest bidder based on the decrypted bid amount. So it just ensures privacy, censorship resistance, and also fairer competition as well. So because the bids are not in plain text, it doesn't sort of sway the bids from other bidders as well in the auction. So some prerequisites for this workshop would be having Node installed and also Yarn installed as well on your PC. So just check if there are any questions. So no questions. So just check if you have Node and Yarn installed, and then clone the Sealed Bid Auction repository as well. And then once you've cloned the repository, I'll then walk through the smart contract. So based on the diagram here, the idea is that we have a bidder. We have the Sealed Bid Auction smart contract. And then we have the off-chain Oracle, which is collecting decryption keys from the threshold network and then passing that on to the smart contract on-chain. So we use Solidity encoding with Ethers.js to encrypt our bid amounts. So for example, it could be 4 Ether, it could be 3 Ether. And when we encrypt the bids, we use the block number, so the auction, the ending block number for the bidding window. We'll use that block number as the condition for decryption. And then we generate the ciphertext. So it's all done using libraries. So we have 2 libraries for Timelock Encryption, which are the BlockLock Solidity library and the BlockLock.js library, which we'll be using as part of the tutorial. Okay. Okay, so just those 2 libraries there. So once we create the ciphertext off-chain, we can then submit the encrypted bid and pay a small reserve price. And that encrypted bid is then stored within the smart contract. Once the bidding window closes, because we've used the closing block number as a condition for decryption, the off-chain oracle automatically sends the decryption key. Once that block number has been mined, it sends it back to the auction smart contract. And then we get the revealing phase of the auction, which is where the encrypted bids are all decrypted. Automatically, it's done all on-chain. And then we can then have a view of what the decrypted bid is as plain text. And at that point, because all the bids would then be in plain text, the contract is then able to work out, as it decrypts each bid, it's then able to work out what the highest bid amount is and who the related highest bidder address is as well. Okay, so the first steps would be to create a folder locally. And you also need to have Foundry installed as well, because we use Foundry to use a smart contract development framework and toolkit. So we use it to compile the contracts and then deploy the contract as well. Okay. So once you create a folder, navigate into the folder, you can then initialize a Forge or a Foundry project. And then, so this part is just steps on pushing to your GitHub repository. So due to time, the next step is to then install the OpenZeppelin libraries, which I've already done. And then next step is then to install the BlockLock Solidity library as well, which we've provided. The link is also in the chat window. I think someone was typing. I think Kwesi was typing. Just see if you have a question. Okay, so in terms of use cases, there are various use cases that could be implemented. Actually, the use cases are at the bottom of the tutorial page. So there's quite a number of ideas. So you could implement so one of them would be a sealed bid auction, which we have in the tutorial. But you can also implement some other use cases as well. So for example, you might have a vesting contract with encrypted vesting schedules. You could also be using governance. So you only release like the governance proposal details or the governance, the voting details. So you don't sway any sort of votes as well. Okay, and then for this sealed bid auction use case, you can also extend the logic to a Victory auction. Some other use cases could be like a sealed wheel, for example. So you can encrypt the wheel, put it on chain, and then decrypt it at a future point in time. So yeah, these are just some of the use cases that we could see as well. Okay, no other questions. Okay, so I'll just talk about use cases as we go along as well. So once you've set up the folder, the repository, you then need to add these lines into your remappings.txt file. And then the next step is then the smart contract. So when you clone the repository, it comes pre-built with the smart contract. So again, some other use cases are like you can have like a delayed payments and escrow contract, whereby the sender could encrypt like payment details. And based on Timelock encryption, the payment details can be decrypted at a future point in time. And then the recipient can then withdraw the funds from the contract as well, based on the encrypted amount. And then you can also have things like Timelock NFTs. You can Timelock NFT metadata and only receive decrypt the NFT metadata at a future block number as well. And even things like preventing front running in DeFi. You might want to have Timelock encryption included in, for example, liquidation bids, so that you prevent things like front running in liquidation auctions as well. So there are quite a number of use cases, including things like time-locked token vesting period for investors as well. So once you've cloned the repository, you have the sealed bid auction smart contract. I'll just walk you through the source code for the smart contract. So the first thing that we're importing is the types library. In the types lib, we have data types for decryption requests. We have the signature scheme ID, the ciphertext, the condition. In this case, our condition is an encoded block number for the bidding closing window. So that's the point in the future when we'll get the decryption key. And then we also have a decryption key, which is received only after the bidding period. And then the signature, a callback address, and the flag to detect or indicate if the decryption has been fulfilled or not. And then the ciphertext is just BLS cryptography points in G2. So in terms of the sealed bid auction, so we import the types lib, just have a custom type for the decryption requests, which includes the custom type for the ciphertext. And then we have a block lock receiver contract, which we need to inherit, just like we did for the randomness contract. So we just need to inherit the block lock receiver because it has functions which we must implement, and those functions are needed because they're called by the off-chain oracle to send the decryption key back to the contract. And then we just have a reentrancy guard from OpenZeppelin to prevent reentrancy attacks in the functions. And then the bidding contract itself, we have an interface for the sealed bid auction contract with different phases. So we place our bid, which is a ciphertext, and alongside we make a small payment of a reserve price, which is why the function is payable. And then we also have a function to withdraw refunds. So that function will be called by bidders who do not win the auction. So the highest bidder has to pay the difference between the amount that they've placed and the reserve price, but other bidders can withdraw a refund of their reserve price at the end of the bidding period. And then we have the function to fulfill the highest bid and a finalize auction function as well. So the fulfill highest bid is called by the highest bidder to make a payment for their bid amounts minus the reserve price. So when we then create a sealed bid auction contract, so in the contract, we're inheriting the sealed bid auction interface, the reentrancy guard contract, and the abstract block lock receiver contract as well. And then we're defining a bid data type, which has the bid ID, the bidder address, the sealed bid, ciphertext, the encrypted bid, decryption key, and the unsealed bid in plain text, and just a flag revealing whether the bid has been revealed or not. And then we have just some other variables just used to track the bid amounts, highest bidder, total bids, and so on. I'll just move into the functions very quickly. So we've implemented a couple of functions. In the constructor, we define the bidding end block number. So this is the block number that we'll be using when we create our ciphertexts off-chain, because for each of those ciphertexts, we'll only get back the decryption key once this bidding end block number has been mined. So that's the condition for our Timelock encryption or conditional decryption. And then we have the address of our block lock contract, which we're using to make decryption requests on chain as well. Okay, and then we just add in the address of the seller as the wallet that makes the contract deployment. Okay, and then we have a function to place a sealed bid. So we're just placing the ciphertext as the bid alongside paying the reserve price. And then just functions to receive the block lock decryption and so on. So I'll just run a deployment to deploy a new sealed bid auction contract. So we deployed it with the sealed bid auction script in the scripts folder. And we're setting the bidding end block number, the bidding window to be 10 blocks. So the end block number would be the current block number plus 10 blocks when we deploy the contract. So the block bidding should be closing at this block number. And then we should have our bidding contract address as well. So just give it a few minutes to deploy. Okay, so the contract's deployed. So the next step is then to place our sealed bid, our encrypted bid. So we can do that using the script. So in the utils folder, we have a script that we use to place encrypted bids. So we just replace the contract address with the deployment address. So you can also find the command for deployment in the README file. So just using forge script. But before that, you need to set your environment variables, which include the testnet RPC URL and your EVM-based private key as well. And then you can get some test tokens from the token faucet, which I shared earlier on in the chat window. So once you deploy the contract in the encrypt and place bid script, we just replace the contract address with the newly deployed contract. And then you can play around with the bid amount as well. So in this case, we just place a bid of 2 Ether. And then that automatically does the process for us. So we make a connection to the smart contract. We then get the bidding end block from the contract as the block height, which will be the condition for decryption. And then we encode the message using the bid amount. And then we get a ciphertext using the BlockLock.js library. And then we're then getting the reserve price from the contract and then adding that to the transaction for placing a sealed bid, because we're going to be using that as a payment to pay the reserve price when we place a bid. So using the encrypt and place bid TypeScript, we can use that to then run a transaction, which calls the place sealed bid function in our contract. So that's just sending the transaction on chain. So it does take a few minutes on the Filecoin testnet. Do apologize. So just waiting for the transaction to get mined. So while it runs, I'll just walk you through again just to recap. So what we're doing is connecting to the sealed bid auction contract, initializing the BlockLock.js library with our wallet and a sealed bid auction, sealed bid contract, BlockLock address, and then it's then getting the block height from the contract for the bidding closing block number. And then when we encrypt, because we're using identity-based encryption, the messages are encrypted towards an identity, which is the decryption block number as a condition. And then we then place the transaction on the blockchain. And from the transaction receipt, we're fetching the bidder address and the bid ID as well. So in this case, we got a bid ID of 136. The condition for decryption is that at block number 2505678, the bid that we placed should be decrypted. So we can check, we can just try to fetch the bid data from the chain just very quickly before it does decryption. So we use the get bid helper script as well. And the bid ID is 136. And then in the get bid, we replace the bid ID with our bid ID. And we replace the contract address with our contract address as well. And then if we run the get bid, it should fetch the bid details from the sealed bid auction contract. So we can see that we have the bid ciphertext on the contract as a sealed bid, and the bid is still currently encrypted on chain. So the unsealed amount is 0. There's no decryption key received yet from the off-chain oracle, from the Randamu threshold network. And then we have the bidder wallet address as well. And the revealed flag for the encrypted bid is still false. And then if we also check, so the bid decryption block number for the bidding closing is 2505678. We can also check on the block explorer for Filecoin testnet, just to check 678. So it's 2505681. Okay, so if we just check that the oracle has sent a decryption transaction. Okay, so there was a transaction just a minute ago. So if we then check the bid data again. Okay, so we can see in this case, we then have the unsealed bid amount. So these all happen automatically without any sort of manual intervention for decryption. So what happens with the decryption is that we get the decryption key at the block number that we specify, the future block number for decryption. Once that block number has been mined, the off-chain oracle then gets the decryption key from the threshold network, and then it calls the receive block lock function. So you can also override this function because it's implemented in the abstract block lock receiver. So depending on your use case, it could be encrypted liquidations in DeFi. It could be encrypted vesting periods. You can customize the receive block lock function such that when the decryption key is received for a specific request ID, you can then tailor it to your needs as well. In this case, when we get the decryption key, we use the request IDs for decryption as the bid IDs as well. So we can just pick the bid data, and then we can call the decrypt function in the block lock contracts to decrypt the sealed bid using the decryption key that we receive. And then because we expect it to be a UINT256, which is what we use to do the encoding. So we encoded to a UINT256 off-chain. When we decrypt on-chain, we also decode back to a UINT256 as well, the decrypted bytes. And then it then calls the update highest bid function for each of the decryption that happens. And that just updates the highest bidder and the highest bid amount as well. If we also check the current highest bidder, so we could just make a call to the contract to get highest bid. But that's a different contract. Okay, so that's a previous contract. So I just call the new contract that we deployed. Yeah, so we can see that we have the highest bid of 2 Ether, which matches the bid data that we received when we made a call to fetch the bid ID. And then we also got the highest bidder as well, which is the bidder address that placed the bid, the encrypted bid for 2 Ether. Okay, yep, so I think that's the sort of end of the tutorial. Right, so there's a question. So the decryption key is in the contract. Who performs the decryption? If you buy that, right. So on chain, when the decryption key is received, there's a validation that's done. So the decryption key is passed to the contract alongside a signature. And that signature has to, have a valid pairing with the public key of the threshold network. So a bad actor wouldn't sort of be able to decrypt themselves, even though they have an idea of the block number. Does that answer the question? So it's a threshold network of chain collaborating to sign, and that then generates a decryption key on the message, as well as the condition, which is the block number. And in a block lock contract, there's an idea of the public key of that threshold network as well. So the signature validation is done on chain for each signature received, and then the decryption happens automatically as well. So you can customize the function for which receives the decryption key. You can tailor it to your use case. It could be encrypted vesting for investors. It could be, escrow contract with encrypted, amounts to transfer at a later block number. It could be encrypted NFT metadata as well, which only the contract can then reveal the NFT details at a later point in time also. Okay. So there's quite a range of use cases that could be built on top of the Timelock encryption on chain.
Thank you very much. We will leave the chat to ask any more questions if they have any last minute. Roland just asked, can you share these links later? And I've said we'll put them in the hacker pack. So don't worry about saving them from the chat now if you're looking to go through and sort of follow along with the recording when you can pause and stuff. That's completely understandable. So yeah, we will share the links. Don't worry about that. I'm assuming no one else is typing, so hopefully everyone else is all good. Thank you very much, Tari, for coming in and giving this workshop.
Yeah, thank you.
Will be available tomorrow for anyone who wants to rewatch and follow along. The same with the Lilypad workshop recording that was in the first half of today's session. So I hope all of you have a good rest of your day. And thank you for joining us again. Tomorrow is our final set of workshops, and they're at a different time to usual. They're at 2 p.m. UTC, so that's 2 p.m. British time, and depending on what time zone you're in, it's effectively 3.5 hours earlier than today's session started. So you can do the maths yourself, but you should also have the calendar invite. So you don't want to miss them. Our speaker is based in Asia, where it's going to be very, very late if they do the workshop at the normal time. So that's the cause of the change in time slot. But hopefully you can still all make that one live. And so I will see you tomorrow. And thanks for joining us again. Have a good rest of your day, everyone.
Thank you.